Hi, I'm Bob. Thank you for working through the exercises with me for the textbook Microeconomics Theory and Applications with Calculus, 5th edition by Professor Jeffrey Perloff. We will address the problems related to exhaustible resources today. We will also tackle the exercises in the challenge section. Here's exercise 3.1. We can sell a barrel of oil today for $P, assuming no inflation and no storage cost. How high would the price have to be next year for you to sell the oil next year rather than now? We can sell the oil today for $P. It equals P times 1 plus the interest rate next year. If next year's price is higher than that, we will sell it next year rather than now. Let's answer exercise 3.2. If all the coal in the ground Q is to be consumed in 2 years, and the demand for coal is as follows in each year where epsilon is a constant demand elasticity, what is the price of coal each year? The expression of the price change from one year to the next is as follows. In a two-period model, we assume the marginal cost of mining is 0. We have a simple relationship between P2 and P1. The sum of the coal sold in the 2 years equals Q. We plug in the demand function for the coal Q1 and Q2. Then we substitute the expression of the price change and obtain the solution for P1. The price change expression gives P2 after we get P1. Let's solve exercise 3.3. Cheese, wine, and cattle become more valuable over time and then possibly decrease in value. Draw a figure with present value on the vertical axis and years on the horizontal axis and show this relationship. So in what year the owner should harvest such a good, assuming that the cost of harvesting is 0. As shown in the graph, the marginal cost curve of harvesting is a horizontal line at 0. The present value of the price goes up over time and then drops. The optimal harvest time is T star, where the distance between the present value of the price and the marginal cost is the largest. It is at the peak of the price curve. Next, let's address the challenge part of the chapter. Here's exercise 4.1. If the interest rate is near 0, should an individual go to college given the information in the figure in the challenge solution? State a simple rule for determining whether this individual should go to college in terms of the areas labeled benefit and cost in the figure. The figure for the challenge solution is for the case of 0 discount rate. An individual should go to college if the area labeled benefit is larger than the area labeled cost. Let's go to exercise 4.2. At current interest rates, it pays for Bob to go to college if he graduates in 4 years. If it takes an extra year to graduate from college, does going to college still pay? Show how the figure in the challenge solution changes. Illustrate how the present value calculation changes using a formula and variables. If it takes 1 more year to graduate from college, the college graduates start to have earnings at 23 years of age instead of 22. The cost area becomes larger and the benefit area becomes smaller. Using math, we consider the change in the present value at age 18. It includes 1 more year of cost and 1 fewer year of benefit. Suppose the cost change is delta C and the benefit change is delta B. The change in the present value is as follows, where I is the interest rate. The change happens at age 23, so we use the exponent of 5 to calculate the present value at age 18. Because delta C and delta B are negative, the change in the present value must be negative. Let's find answers to exercise 4.3. Which is worth more to you? A. A $10,000 payment today, or B. A $1,000 per year higher salary for as long as you work. At what interest rate would A be worth more to you than B? Does your answer depend on how many years you expect to work? We compare the present values of the payments. The present value of a $10,000 payment today is $10,000. The present value of $1,000 per year future salary for T years is as follows. We consider 3 cases. In case 1, we assume the future per year payment is forever. The present value of future payments can be simplified to 1,000 divided by the interest rate. When the interest rate is 10%, the present value of the 2 payment methods are identical. When the interest rate is less than 10%, the present value of the per year payment is higher than the lump sum payment. The future payment method is worth more because we place more value on future payments. When the interest rate is more than 10%, the present value of the future payments is less than the lump sum payment. The lump sum payment method is preferred because we place less value on future payments. The break-even interest rate is 10% if we expect to work for a very long period. In the second case, we assume that the years of working cannot be seen as infinity. The present value of the future payments is smaller than that in case 1. The break-even interest rate or discount rate should be lower than 10% because we need to place more value on future payments. In case 3, we assume that the interest rate is 0. We place equal values on current and future payments. In this case, the present value of working for 10 years equals the lump sum payment. If we work for more than 10 years, the per year payment is worth more. Let's tackle exercise 4.4. In 2012, the school paid its starting teachers $38,087 with a bachelor's degree and $41,802 with a master's degree. For simplicity, assume that these salaries stay constant and do not increase with experience. Suppose you know that you want to work for this school and want to maximize your lifetime earnings. To get a master's degree takes 1 extra year of schooling and costs $20,000. Should you get the master's if you cannot work during that year? Should you get your master's degree if you can work while studying for your master's? In your calculations, assume that you will work for 40 years and then retire and consider interest rates of 3% and 10%. We use the net present value approach to determine whether getting a master's degree increases lifetime earnings. The net present value of working for 40 years if we get a master's degree is as follows. If we cannot work while studying, the first term, pi 0, is the cost of getting the degree, including the tuition and the foregone earnings. The other terms are the benefits of getting a master's degree, that is, the difference in earnings. Using the formula for the sum of a geometric series, we have the following expression. If we can work while studying for the master's, the cost only includes the tuition. The net present value of getting a master's degree will be as follows. In the first case of an interest rate of 3%, we compute the net present values and find that both are positive. It implies that no matter whether we are allowed to work while studying, we should get a master's degree because it brings a positive net present value. The second case is when the interest rate is 10%. The net present value of getting a master's degree is negative if we are not allowed to work during the year studying for the master's degree. It implies that we should not get a master's degree because it brings a negative net present value. However, if we are allowed to work during that year, we should get the degree because it gives us a positive net present value. In this exercise, we can get the same conclusion if we assume the payments are forever and simplify the calculation. Thank you very much for watching this video and solving all the exercises with me for this chapter. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.